today's talk, so I've designed the talk keeping in mind the audience, and my understanding is that there's a mixed audience in today's lecture. So I've tried to design it keeping that in mind, and as you'll see, that there will be ideas, concepts, and methods from both statistics, data science, as well as from other related fields such as machine learning. And that starts immediately on the title of today's talk. So the objective here today will be for us to learn about learn from data, and we aim to learn from data, but what we're after is to learn about something I'll refer to as interval trend lines, and this is the main parameter of interest, if you will, a parameter in terms of statistical terminology. This is our main target. This is exactly what we're after. This is what we would like to learn from data. This is work I have been developing with my collaborator, Gabriel Martus, who was my former postdoc and who is currently an assistant professor at Universidad Torquato de Tella in Argentina. Okay, so in terms of buzzwords, that's the buzzwords that I really want to for you to keep in mind. Interval trend lines. This is a range of data. We aim to learn about these parameter of interest. And what is our take? How do we aim to approach this? Let's move forward. So the way we will be approaching this problem is via something that is known in the forecasting literature as singular spectral analysis. So this is a methodology that has been receiving considerable attention in recent forecasting literature. And well, why and where have been as this methodology been appearing? So let me give you some examples of some papers that have been exploring ideas on singular spectral analysis related methods, and I'll focus mainly on the forecasting literature. People in the audience may have contributed also elsewhere, but my main focus here today will be from the point of view of prediction, and in terms of outlets that would be on that field, such as the International Journal of Forecasting, as well as the Journal of Forecasting. So these are two outlets that are quite that are international forums where people have been publishing results on forecasting, and some recent contributions on singular spectral analysis based methods are just mentioned there. So, and as I mentioned earlier, there's more people contributing even outside of these outlets, and this is a literature that has been approached in other fields of science, including, for example, engineering as well. Okay, so for now, this is the buzzword. We're just at the introduction. So this is my the methodology I want you to keep in mind, and this is the methodology that we'll be developing and extending here today. So we'll be using singular spectral analysis in order to learn from data about interval trend lines. That's the target for today. Okay, so let's move on. What's actually justifying the rising popularity of SSA? Let me comment on that. So SSA is both naturally tailored for forecasting as well as for decomposing non-stationary time series. So which is quite appealing, because in this you have, in a single technique, you are already having the power to build and to construct predictions, and at the same time you have a tool that you can use for decomposing a time series, and you don't have to pre-process them. So they just come in their raw form, and they can be clearly non-stationary. Okay, and you decompose this series into what? You decompose them into a set of principal components. So that's why many people have advocated that single spectral analysis can be regarded as an extension of standard PCA to a time series context. Okay, so and what is the meaning of these principal components? How do they look like roughly? So essentially, these principal components, they may look just like a trend. So you may have a principal component that would simply look like a trend, which is ideal if you would want just to extract a trend. So that's a but at the same time, some other components will be associated with cyclical movements, regular movements, such as, for example, business cycles, which are quite studied in economics, or some other regular movements of interest as well. So, or you might actually still extract with single spectral analysis another series of components that will correspond to noise. So just very high frequency components that, I mean, from a statistical point of view, they actually are just something which is not contributing to the signal. Essentially, for signal is in terms of what we preserve in here in terms of trends and cycles, and that's essentially what SSA aims for in terms of these, in terms of the intuition behind the methodology. Okay, let me give you some flavor in terms of moving from intuition into being a bit more precise in terms of how it achieves that, how it decomposes non-stationary time series into principal components. This will be still very elementary, okay? So this is, I mean, it's not even fair calling it an SSA 101. So it's a very rough introduction to SSA. And the idea, the first steps of SSA, so you can regard almost SSA like an algorithm. And the idea is as follows. Is you start with your raw data, with your raw time series, okay? You have n observations, you have your time series, and you move that time series into what people in this field call a trajectory matrix. And the trajectory matrix is essentially given by the following. It's given by you partition your data into blocks of size L, such as this one, and then you keep doing that for the following period and so on. So you have K blocks of length L, okay? And essentially what you have are just K versions of your data, K subsets of your data, if you like to phrase it like that. And then what you can do is to apply singular value decomposition. And what is singular value decomposition? From roughly speaking, singular value decomposition is just a linear algebra methodology that allows you to essentially to separate a matrix and to decompose it in this way. Okay, so the idea then is the following. Let's recap. You start with your raw data and you move it into this trajectory matrix, and then you decompose actually your matrix in using singular value decomposition in a way that I'll make precise in a second. And what then you will want to do is actually to just reverse that process, because some of these elements in here, some of these elements in this sum will be the ones that will be accounting for trends. Some others will be accounting for cyclical movements, whereas some other will be responsible for noise. But of course, it goes without saying that it is more complicated than that because this is still a matrix. But the idea is just, okay, we move into this space of matrices, and there we know how to, we use linear algebra to decompose this object, and then we want to move back into the space of time series. That's roughly the idea. So, and let me just introduce here some terminology. L is the window length. It's if you will, it's just a smoothing parameter, and you have here the eigenvalues of this matrix, which is given by the product between Y and Y transpose, as well as the corresponding eigenvectors, which are given by U1 to UL. Vi is defined in this way, and D is essentially just the number of positive eigenvalues that you have. That's it. That's essentially just the mechanics, if you will, behind SSA. And then I'll as we move along, I'll elaborate a bit more on making this a bit more precise. But these are the building blocks. These are the steps to get started with SSA. Okay, but so what is the goal of today's talk and of this paper? By the way, I should mention that the paper is in press, so it has been accepted at Journal of Forecasting, so it will be available soon, and in the paper there will be more details. So in this talk I'll concentrate on actually the highlights, and the main goal of today's talk will be essentially to develop SSA methods to model and forecast interval time series. And interval time series will look like this. So essentially, per each period of time, you have an interval rather than having just a scalar. So that's essentially what it is. So per period of time, you actually have an interval. Okay. So, and there is an increasing interest on interval time series. I'll just mention first a few references, and there's contributions also on interval valued data analysis and on symbolic data analysis more generally, including contributions from even people here in today's room, here in the audience, I meant. Okay, so these are just some recent contributions in terms of interval time series or interval valued time series, as you prefer. Okay, so but what's really, why do we care about interval time series? Well, they are natural for modeling the dynamics of a range of values. Okay, so whenever, rather than just modeling the signature of a certain process of interest, whenever you have to model a range of values over time, that's when interval time series become key. And let me give you one example: intervals of prices during trading sessions. So, well, there's a low and there's a high, and that is, you have a stock market, you have a trading session, and prices will oscillate over time. And you can record just low as well as high, and with that you get a daily interval rather than modeling just prices over time. Okay. Well, it is by now well known, and this is a well known fact by now, that what happens. Well, you could consider naive midpoint analysis. That is conceivable, but you would simply ignore internal or within variation, which, for example, in the case of this financial example I was mentioning earlier, that would correspond to ignoring intraday variation. That is, well, prices will be oscillating. If you just take low and high, you will be essentially just ignoring all the variation that would take place in a day, and that is something you would not be accounting for with a naive midpoint analysis. So this is something that people have explored, but it's obviously a naive naive take on this. If you want to think about other examples, so even while we were just having this informal chat before the talk started about even temperatures and the way that temperatures evolve over time. And of course, we can also think about low and high in terms of minimum and maximum daily temperature. But any naive midpoint analysis will simply be ignoring the intraday variation also of temperatures over time. And I mean, the literature is essentially aiming to target precisely these kind of problems where you want to model dynamic of a range of values. Okay. Now, so I mentioned that the target here today would be to equip singular spectral analysis with the ability to learn from interval, to learn about interval valued trend lines. So how do we go about that? Well, we will resort to ideas and methods from a field of statistics known as symbolic data analysis. And this will be the starting point for us to take on board the interval valued nature of the data. Okay, so this is a field that is quite general. So and where the type of data that we can work with are more general than just scalars as we typically work in other fields of stats. And this there's, as I mentioned, there's experts here in the room in terms of working on this field, including for example, Paulo Breto, who has worked quite a bit on this topic. Okay, now my focus here will be mostly from the interval valued, from the time series of intervals, and so I'll be focusing mainly on that aspect. But in any case, I'll need to resort to some tools from symbolic data analysis, and I'll mention precisely those later on. Okay, so now well, it's what we aim for in here is the development of a symbolic version of singular spectral analysis. Okay, so this is essentially what we're aiming for, and the ultimate goal would be for us to, we have an interval time series and we would like to decompose it in a sequence of set-valued stochastic processes. That is, a set-valued stochastic process is just essentially just a collection of intervals, of random intervals over time. And that could be ultimately used for modeling just the low and high in terms of the financial application I mentioned earlier. So the idea would be for us to gather everything into components that would correspond to interval valued trends, interval valued cycles, okay, as well as interval valued noise. So think about the following. So as I mentioned earlier, if we think about trends and cycles as part of our signal, essentially now what we have is that rather than having just a time series just as before, now we'll start to get things that would have a certain dynamic over time, but that dynamic would itself be an interval. Okay, so we can start thinking about, okay, maybe there's a trend line that looks like this, and that is what we'll call an interval valued trend line. So we're really trying to track in your interval valued signals with this method. Well, we would like to decompose and forecast as well a set valued stochastic process. Okay, that will be our unit of analysis. It's just a collection of random intervals ordered over time. Think of just the stock market example to make this concrete, if you'd like, and we'd like just to decompose these things and to use these in a way that it could be used for learning about trends and also even in terms of forecasting. Okay, so let me comment on the following as well. There's an R package that can be already used to implement the proposed methods. This is a package that we are developing, and it is already available from CRAN, and that it implements the proposed methods. The two main commands I would like to highlight in here are this one. This is the command you can use for fitting an interval trend line from data. This is it, ISST. And there is this ITS frame, which is an object. This is the sort of core object that it takes, and it's essentially just an interval time series frame object that we developed also on the package to implement this. Okay, so there's more on the package as well, more developments that we've gathered there. So in case you're curious to explore, please just install and feel free to examine it. Okay, well, let's see. This is just one example. The example, this is just our code. Sorry, our code with this example. So for our code that we use for implementing the figure that appears next, and we're just loading here first the data, just moving everything into this ITS frame object, and then just fitting everything. It looks like this. So this is the final product, if you will. This is what this code would yield. It would produce this interval valued trend line here being depicted over time. Okay. Right, and I'll come back to the data here. I'm being silent in terms of this data set, but this is also the data set that we'll be using in later on the data illustration. So I'll come back to this later. Okay, so this is it. This would be a final outcome of using these methods. So there's data in the form of set value stochastic process. And then in this case, we're just learning about the corresponding interval trend lines. I can anticipate that essentially these are actually intervals that would, the data that we're using in here is also data from a financial application where we have lows as well as highs on a stock market. Okay, let's move on. So we're done with introduction and motivation. That's complete by now. So we're switching gears now, and I want to be a bit more concrete. I've told you about what the aim is. I would like to tell you how we've reached that aim now. Okay, so I'll introduce some details on symbolic singular spectral analysis. I'll be relatively brief. There's more details also in the paper, but I'll try to give you the main intuition about the ideas underlying the method. Okay, so this is where we're going now. Okay, so there's also at the end there will be a real data illustration, and there I'll offer also some closing remarks at the very end as well. Okay, so let's start. Before introducing singular spectral analysis, symbolic singular spectral analysis, let me first introduce you to the symbolic covariance matrix. Okay, so this is an interval valued data matrix. So you just have a matrix whose entries are actually intervals. Okay, so there's P columns there. Okay, and each of these entries is just an interval. Okay, we could make this more complicated, and rather than having just intervals on the real line, we could even have more complicated objects. Let's just leave it there. Okay, and let's just think how we can actually compute elementary statistics about this object. Well, it has been derived the following sample mean of the jth column, which is essentially just given by the following expression, whose intuition I'll comment in a second. Essentially, what you have is that this is you're taking an average, right, of all these guys in this column, and it's a double average, if you will, because you're also averaging here over the lower value A as well as the upper value B. Okay, so it's a double average, if you will. Okay, this is still from an intuitive point of view. This makes sense. It's very easy to get the intuition on this object. So it's like a double mean, if you will. Well, it's less simple to think about. Okay, and how would a sample covariance matrix would look like from a symbolic perspective? And this is something that has been studied and introduced, and it is documented, for example, in these papers I'm mentioning in here. Okay, so you can also construct a sample covariance matrix that is tailored for this type of object in here, this interval valued data matrix, and this would be how the entries of the corresponding covariance matrix would look like. Okay, so this is a main ingredient from the symbolic point of view for what we're doing here, and it is a main ingredient for what we'll be doing in here from the symbolic point of view. And let's move on. Let me also introduce you another object of interest, which is something to which we'll refer to as a matrix of ordered pairs. And a matrix of ordered pairs is essentially it's just like it's a special case of a partitioned matrix. Well, essentially it's just a matrix whose elements are ordered pairs. And for reasons that may become apparent later, I will also need this type of matrix, this type of object. I'll need to introduce it now as well. Okay. Okay, so with this matrix of ordered pairs, questions start appearing. How are we defining sums? How are we defining subtractions in terms of this space? In terms of this space of matrices of ordered pairs? How do we add up on this space? Okay, so, and for the purpose of this talk, I'll be essentially just considering pointwise Minkowski type counterparts in the sense that it's like we're just adding up here pointwisely each of these components. So this is the geometry we'll keep in terms of these matrices that were introduced here in terms of the matrices of ordered pairs. Okay, and where also this is both A and B are also matrices of ordered pairs as well. Okay, so we add them up. It's still a matrix of ordered pairs, and actually the sum in this case would be essentially just given by that. Okay, now of course we would like to, I mean, matrices of ordered pairs should not be our final target, because remember that we really would like to be able to just stay on, also take the interval valued nature of the data into account. So we'll also be having set valued functions in here, and I'll be also using this mapping in here, and this mapping there, it's important. It will allow me to just move everything into an interval, and it will always be allowing me to, in cases where things would not be well defined as an interval, I adjust for it by using this operation via this set valued function. Okay, so that's essentially just an auxiliary set valued object that will be allowing us to move from pairs just also to intervals, and to always have everything well defined on the space of interest, which is the space of intervals. Okay. Okay. In terms of norm, well, we have to have a length for these objects in terms of these matrices that we're studying in here, and we'll be using the following norm, which is just a version of Frobenius norm. So in particular, you'll see that if A and B were actually the same, we just recover the standard Frobenius norm, and this is a recurring topic. This is something that we would like it to happen, and not obviously that this doesn't happen just there. It would also be the case in terms of this guy in here, okay? Even in terms of the corresponding symbolic objects, if A was equal to B, we would simply be recovering just the standard sample mean here, if A was equal to B, and we would be just recovering the standard sample covariance matrix if A was equal to B. This is something that the proposed methodology will also obey. That is when we it will become apparent next that when A is equal to B, that is when the interval degenerates into just a single observation. What we actually have is we just get back to singular, to just standard singular spectral analysis methodologies. Okay, right. So this is just warm up. Okay, and in terms of warm up, there's two things. Let's recap. One thing is symbolic covariance matrix. Okay, it's just adapted to the interval valued nature of the data. Warm up number two, it's just okay. Let's just be careful about the setup that we have in mind, and there's these matrices and the corresponding operations, as well as the set valued function that we've introduced to move from pairs also to intervals. Okay. Let me now start introducing singular symbolic singular value decomposition. Okay, so the starting point, the unit of analysis, if you will, is this interval valued time series. So we have an interval valued time series, and we will want to just revamp singular spectral analysis in a way that it is adapted to this setup. Okay, so let's get started. And we've already discussed embedding, and embedding is essentially just moving the raw data into a trajectory matrix of ordered pairs. Okay, this is very similar to what I've discussed earlier in terms of just plain vanilla SSA. Okay, and note that exactly just like plain vanilla SSA, what we're having in here is just, we're just transforming the raw data. We're actually just taking pieces of the raw data and these pieces are again of length L, and we have K pieces that we're partitioning the data into these different chunks. Okay, so just some terminology. L is the window length, as I mentioned earlier, which is it's very similar in terms of role to what is known as the bandwidth. Okay, so think of it as a bandwidth. So it's just a smoothing parameter, right? So we have these matrix of ordered pairs, and note that the raw data is just contained in here. So, or just contained in there if you prefer seeing it from that angle. Okay, so that's where the raw data is. So embedding, stage number one, you just move all your data into this trajectory matrix of ordered pairs. Okay, stage number two, you would like to decompose, and you would like to decompose, but you know you will want to take into account the interval valued nature of your data. So this is where the symbolic data covariance matrix comes again. That's the S I've introduced earlier. And what we're aiming for at this stage is essentially to conduct a singular value decomposition that takes into account the symbolic nature of the data. So it's very similar to the step we were mentioning earlier, but where now essentially we just have to keep into account that S is symbolic rather than just built from a standard time series object. Okay, so same game again, but now you have to take into account the covariance matrix for symbolic data S and do your decomposition in that way. Okay. With step number 2, we get a decomposition, but we're in a space of matrices. And what we want in the end is a time series. So we have to group, well, we have first to understand what is signal and what is noise. And that's what we do at the grouping stage. So at this stage, we aim to separate signal from noise. And essentially what we aim for is, okay, so y is equal to the sum of all the yi's, and we just want to preserve some of those yi's. We don't want all these matrices, so just the ones that are containing signal, and we'd like to get rid of those that are not accounting for noise. So we'd like to just focus on this guy there because we want to learn about trend lines. Okay. How do we do that? Well, we extend an approach based on the periodogram that we've proposed in 2020, but this extension is adapted to an interval value time series context. So roughly speaking, the idea is to build a periodogram from the interval valued data, and then just to resort to the method we've developed earlier. Okay, so I'll give more detail on that. Okay, so for now, just think about the following idea. We want to learn about this set I that tells us how many components we're keeping in order to separate signal from noise, and I'll give a more detailed account on how we achieve this using the periodogram-based approach in the other paper. Okay. Okay, after this step, we understand what would be the signal. So, but again, we're still in the space of matrices. How do we go back to a time series? There's a step. There's the final step in singular spectral analysis, and that step here is moving you back into a matrix. Okay, so just a minor comment. This is the running title here. This should be analysis in here, not decomposition. That step was done earlier, of course. Right. So what we're doing with diagonal averaging is the following, and this is standard in this literature, and it is the idea is we need to move back from these matrices yi into a time series. So what we do is first we need to look for the matrix whose anti-diagonals are constant, and those are called Hankel matrices. I'll take note of that just because it might just appear on the slides later on. So think of an Hankel matrix as precisely a matrix that is constant over whose anti-diagonals are constant. Okay. So, for example, the matrix we've presented earlier is an example of an Hankel matrix. Let's just recap that. So, when we have here y2, y2, y3, that's perhaps that's too much. Let me just clean that. Okay, so what's happening here in terms of, and I'll stop in here because this is already more than enough. what's happening in here is that this matrix, the anti-diagonals are constant. You have y2 here, you have y3 there, you have y4 there, etc. So this is an example of an Henkel matrix, okay? And this is what we want to do now, because we would like to go back into an Henkel matrix. So to get back into a time series, we want to learn about the time series in the end. Okay, so what we do then is precisely that, because because if for s equal to 2, that is when you have y plus j equal to 2, essentially you just have the first entry on your matrix, and for you to have an Henkel matrix, well, you just essentially just take the element that is given by, it's just giving you then the interval A1 B1 prime. Okay, now let's move into s equal to 3. S equal to 3, now you have two entries, so you're looking for the anti-diagonals that were appearing here earlier. So this is where we're at the moment. Okay, so this is essentially just where we are at the moment. So y plus j equal to 3, I meant. And in that case, we're just applying this mapping, which will be essentially just giving you just the corresponding average of those pointwise entries. And the phi in here, I recall, is just, you may ignore this phi if we were just always having everything well defined, then this would correspond to that, and this phi will get everything to always be well defined as an interval at the very end, because phi, this set valued function, was exactly built in keeping that need in mind. And we keep moving on, and we would get the same thing. So this would bring us into an Henkel matrix, and from an Henkel matrix, then we get at the very end a time series. So at the very end, you can keep doing this, and essentially, if there's this general formula that would allow you to just move back into an Henkel matrix by using your interval. So producing your Henkel matrix via this mapping that is defined in this way, which extends precisely this idea of just averaging over anti-diagonals, so to produce an Henkel matrix. Okay, and that's the way that that's the beauty of it. That's the way that then you move it back into the space of time series. Okay, right. So now I'll be very brief here, but I just want to give you some details. I want to then get back to the application. I'll be very brief here. Essentially, just the idea in terms of these are more details in terms of grouping. This is just using a Kolmogorov-Smirnov test based on the cumulative periodogram of the residuals. So this would be standard on any course on spectral analysis or on time series analysis. The idea is essentially just to assess the cumulative periodogram of the residuals and to see whether they are similar to what you would get if you just add white noise, and white noise would simply correspond to the diagonal. Okay, so we just the algorithm then it just goes like this. You keep adding components until your residuals essentially just until you stop rejecting your null hypothesis, in which case you would stop. Okay, so again, this would be detailed also in the paper, and if you want to have a look at the most elementary version for just standard time series, details are in this paper. Okay, so I'll be also brief in here, but I need to say this. I mean, I need to justify this procedure in terms of diagonal averaging on this setup, because it's not so obvious that this should be the right way to move back into the space of matrices. So I want to just give some brief details on this. Okay. So again, this is the space of all Hankel matrices of ordered pairs. Again, just think of it as matrices whose antidiagonals are constant, such as the trajectory matrix, for example. And what can be shown is the following. So if you start with a matrix of ordered pairs where you have your raw data, and if you would like then to assess what would be the closest element, closest edge in the space of Hankel matrices of ordered pairs, well, what happens is that the closest element is simply given by taking the corresponding averages over the anti-diagonals, as can be seen from here. So, and this is similar to what already appears in terms of standard singular spectral analysis. And I must stress that this is the norm, of course, plays here an important role. Okay. Okay, so that's it in terms of technical details. I just want to give you now some comments on predictions that can be built over this method. So you can still construct a recurrent forecasting algorithm. And the idea is as follows. So the idea is to equip still SSA with an autoregressive type of assumption, so that the I've observation can be seen as a linear combination of the previous L-1 observations, and in this sense, okay. And if you, so keeping in mind this recursive structure, predictions can be made after we learn about alphas, and there have been different ways that have been suggested in the literature, so to learn about such coefficients. Okay. Okay, so of course, just making this a bit more concrete is that of one-step forecast can be made via a combination of the most recent L-1 interval valued signals using the previous specification, the previous autoregressive specification. And this is just making concrete what I was mentioning earlier. Now, where these guys, the tildes, remember that the tildes are coming from the step of diagonal averaging. Okay. That's, of course, this is just one step ahead. You can define the same thing in terms of out of sample forecasts for the remainder time periods. Okay, in the time that I have available, I'll illustrate the methodology on a case study on a real data application. And I would like to stress once more that I've tried to offer you the highlights, and there's also more details that are included in the paper, including a simulation, Monte Carlo simulation study, also to examine the finite sample performance of these methodologies. Okay. Okay, let's move on. So this is the data illustration, and we're back to the Merval index. Remember, we've had some code previously, and the code was actually first loading the Merval index, which is the principal index of Argentina stock market. It's a sort of analog of CVINT in Portugal. So it's just an index describing activity of stock market, and that's the Merval. Okay, well, what's the time horizon? It's 2016 to September 2020. That's the time horizon, and the frequency is weekly. So we're considering weekly data. It obviously we could have considered also daily data, even lower frequency as well would certainly have been interesting. So for illustrating the methodology, we've just focused on weekly data though. Okay. Variables of interest are the lows and highs that I mentioned earlier. So we're focusing on minimum and maximum values weekly, and the data were gathered from Yahoo Finance. Okay, right. Okay, so let me just mention some noteworthy events. So in 2018, so that's when a currency crisis started in Argentina. So, and there was an IMF intervention at that point. And this is just some I'm just referring here to second quarter and third quarter, because so first quarter, it was generally when the currency crisis started. So the IMF intervention then just was approved in second quarter, and then it was actually then measures had to be reinforced, and so their intervention was increased by $7 billion later on. Okay, so why am I mentioning this? This will appear also on the case studies. I just want to contrast also the trend lines that we get, also with some events that clearly were playing a role on at least on the media, and then whether I'm just having a look at on whether they on whether there's anything that we can see on our trend lines that that has a possible relation with these noteworthy events. Okay, so but this was a major event, this IMF intervention. Another noteworthy event on the Argentina economy was the Paso. So in Argentina, you have primary elections, and the Paso is essentially the expression that is used to denote such elections. And there was a very surprising outcome. This is documented even in the media. Well, and it was surprising, so unexpected. And definitely that led to at least some noise on the media. Let's see how it looks like in terms of stock market as well. Okay, so I'll comment a bit more on the Paso, but first I want to mention that in 2020 there was a sovereign debt restructuring process taking place, and well, we all know that then, yeah. We're in the age of COVID, and certainly that might also have had an impact on stock markets. Okay, so I'm just so there's in terms of Paso. So the unexpected point, just to highlight, was precisely related with Christina Kirchner in terms of the corresponding the polls did not expect her to do so well by then, so that was a surprising outcome, and it led to some discussions also as well. Okay, I'm not commenting more on that. I'm not an expert on political science, so I'll stop there in terms of commenting on this. Okay, what I want to show you now are the trend lines that we have that were extracted using our methods. So in gray, you actually have in gray what the raw data, okay? And there's two approaches that we've devised. Think of these just as the same version. It's just interval value time series singular spectral analysis. But the smoothing parameters are just changing, okay? So the red line is using the periodogram-based approach that I've mentioned earlier. And we've also discussed in the paper another way to smooth, which is based on the Hausdorff distance, which is a distance between sets. It's a standard distance between sets, okay? And that is displayed there just in blue, okay? So that's this one, okay? So that's the one based on Hausdorff distance, whereas the other one that follows the data quite closely is the one based on the periodogram. Okay, so and this is, let me emphasize this. These are post-mortem interval trend lines. Okay. What I want to show next are the corresponding first principal components. Okay, so the first 12 reconstructed components. So this ERC there is just denoting elementary reconstructed components. So it's and the first one you can see there that the first one is essentially just an interval trend line. This certainly would still be related with the trend line or a very slowly moving regular component, and you start seeing that well, there's components such as this one that okay, they still may be related with a cyclical component, and as we move along, if I was showing you the remainder components, they would start really oscillating more and more. Okay, so that's essentially how it will look like. Okay, now remember that the goal was to learn about interval trend lines, so we can do that by adding up the corresponding interval trend lines. For example, if we just added up this one and did diagonal, well, this is already after diagonal averaging. Sorry about that. So if we just focus on this one, this would be just a trend. Well, we might add these two together, etc. So remember that grouping is what will be telling us where essentially just to stop. Should we sum all of these? Should we sum all of these? Should we just add the first two, etc. Okay, this is what we get in terms of grouping, and I'm that's precisely what I'm implementing next as well. Okay, so using the periodogram type of method as well as the Hausdorff distance type of approach. But now I'll focus on real-time analysis. So rather than just doing a post-mortem, I'll be doing this in real time. So this figure is exactly the one we've had before. But now let's see if we remove this, the last quarter here, and if we try actually to learn about this in real time. So you see that this is I mean, performance would be okay in terms of disentangling the time series, and in terms of extracting also the components. But I mean, this is just naively thinking. It's obviously not taking into account all these ups and downs. So it's not surprising that prediction in here it's not great, because this trend line is not taking into account all these irregular movements that we're having there. So if we move here, we're starting to have prediction just having data until this point, and well, it becomes a bit better, but of course it should be kept in mind also that performance may look just like in there. But again, this is not surprising, keeping also in mind that the Hausdorff distance-based criterion is definitely not taking into it, is more looking into a trend line that is not following the data as closely, and of course this then justifies what we're seeing there in that chart. Okay, so this is essentially the same thing, and keeping time constraint in mind, I'll move quickly over this. This is essentially just doing just one step ahead predictions in real time, just first having data just until the third quarter of 2020, and then just predicting year and so on. Okay, so and this then would be the predictions with data just until early 2018, and then doing a prediction for the forthcoming quarter. So this would be the corresponding real-time performance of the methodology. Okay. Okay. So now let me just finish. So one of the main goals of this article was on extending singular spectrum-based analysis to an interval time series context. I think it's fair to say, personally, at least I'm very happy about the trend lines and also about the way we learn about trend lines. I clearly think there's room for improvement in terms of the corresponding predictions, but though I think it's a challenging problem, perhaps we would need to get the corresponding dynamics of the recurrent forecast algorithm to be more complicated in order to reach perhaps better predictions. This is just unknown to me at the moment. The proposed extension is tailored for modeling a range of values. So to learn about interval valued signals, and yes, you can still get out of sample forecasts of said range of values. And the proposed method will coincide with standard singular spectral analysis when the data of interest are themselves standard time series. On the paper, we also explored the multivariate version, and the multivariate version actually allows us to combine both time series, standard time series, as well as interval time series. So you could have just a standard time series as well as an interval value time series and try to model both at the same time. That's doable using this methodology. I'll stop here. There are some ideas for also for extensions. Thank you so much. I'll accept your questions.
Okay, thank you very much, Miguel. It was